Uh, am I audible? Hello.
Yes, sir. Audible, sir.
Yes, sir.
Yeah. So good morning to all.
Good morning, sir.
Okay. Now,
Good morning, sir.
yeah. Good
Morning,
morning.
sir.
We are going to discuss today the task communication, and I'll be sharing this itself as the recorded video for you people. I won't be making one more recorded video for this. So the same thing will be shared as the recorded video. Uh, In the previous session, you understood about the process. Now, I request everyone to mute. Please, all of you mute. Only when you have doubts, you can raise your hands or you can unmute yourself and interrupt me. So, till that time, I want everyone to mute and just listen for me. So, just maintain the diagram of the online presentation. Previous class, we discussed the task, processes, and the threads, and you also understood the basic differences between the process and the thread. So, process is heavyweight and thread is lightweight. So, why process is called heavyweight? Because every time you create a new process, a separate address space is created for that process. So you can make a process create any number of duplicate copies of itself. Every time a duplicate copy is created, so there is a separate address space created for that also. And the duplicate copy that is created, you can call it as a process. Now, since there is a separate address space created for every process that is created, so it's called as an heavyweight because when the CPU is switching from one process to the other process, you got to change the address space as well. Now, whereas the thread is lightweight because its execution is much faster. Why it executes much faster? Because threads, say all the threads, they live within the same address space. Say, for example, I load one address space into the main memory and I can go for creating any number of threads for that process. Now, all those threads, they live within the same address space. That means they will be the same code section. So they'll be sharing this same each section. They'll be sharing the same data section. Only thing is they will be having their own TCP. That's called as thread control block and the stack. So stack and TCP will each process with each thread will have their own copy. So the rest all will be shared. So you make 100, you create 100 threads within the process. All the 100 threads will be running by sharing the same address space. And when you make the CPU switch from one thread to the another thread, you don't have to change the address space. So address space remains the same, and the CPU can be made to switch easily from one thread to the another thread. So hence we say the thread execution is much faster, and each thread you can designate to execute some part of the process. So that is what is thread. Hence it is called as lightweight process. So now these are all the things what we understood in the previous session. Now we are going to discuss today the task communication. So task or interchangeably you can also call it as a process. Process communication. How one process is going to talk to the other. This is what the topic is all about for today. Now, task communication is very much required in a multitasking system or a multi-processing system. So you within a multi-tasking system, you require one task communicating with the other task, because those are the tasks of the same system ultimately, getting executed. So there may be a need for one task to communicate with the other task. Or these are all the tasks of some application, or the processes of some application. And some point of time, there may be a need for one process to talk to the other. Now, what is the meaning of talking here? The meaning of talking here is exchanging the information. One process exchanging the data with the other process. So that is what we call it as inter-process communication. One process talking to the other process. So here in the programming terminology, we call it as inter-process communication, or short form, we can also call it as IPC. Now, and again, multitasking we're using just to achieve the parallelism, because I want to perform more things simultaneously or concurrently, so then I go for using the multitasking system just to speed up the process. Now, the processors or the tasks running on the OS, we can be they can be classified into two types. One is the cooperating processes, and the other one is the competing processes. Now, what are cooperating processes? So these are the processes which will share the inputs, so or which shares the data, which exchanges data with the other process. So that those processes we call them as cooperating process. Or in other words, say that the process, the first I have one process executing, so that finishes its execution and gives some output, and that will be fed as input to the next process. So output of some process is given as input to the other process. So some kind of what information exchanging is happening between the processes. So those processes we call them as cooperating process, because so they execute by sharing the information among themselves. Now, the other type of process is competing process. Competing process here also, they share, but not the data, but they share the resources. And why they're called as competing processes here? Because they compete for the resource. So because we have limited resources in the system and you can have n number of processes running, so there is a need for a process to compete for the resource allocation. So this is here, when I say competing processes, they are not actually involved in sharing the information or the data. They are involved in sharing the resources. So what kind of resources they are sharing? So they can go for sharing the file, display device, or any other physical device. So next, cooperative processes exchange information and communicate through the following methods. Now, what they do? Cooperation through sharing, that is exchanging the data through some shared resources. So there are many mechanisms for making the process exchange the information. There is something called as message queue, there is something called as pipe, there is something called as shared memory. Now, using all these mechanisms, you can make one process exchange easily the information with the other process. Now, cooperation through communication. This is another form of cooperation. That is, here we don't have the data being shared here. Now, then what is the cooperation here? The cooperation here is the execution synchronization. When I say cooperating, it need not be always for sharing the data. It can also be for synchronizing the execution. Now, why? Because when I say a resource is being shared by multiple processors, you require a controlled access to that resource. So when a process is accessing the shared resource right now, we should not allow any other process to access that shared resource until this process, which is currently using the shared resources, releases it. So this kind of synchronization should be provided, when, especially when it is a shared resource, some kind of synchronized access to the shared resource is necessary. So if synchronized access is not possible, so then the programs they behave incorrectly, or they behave abnormally because they don't have the proper access to the resource, and all of them will behave incorrectly. Ultimately, the application will hang up, or the application may get corrupt. So this is what cooperation through sharing the information or the data, cooperation through communication. Now, how do you make two or more processes communicate and synchronize in order to access the shared resources? So now the mechanism of doing all these things, sharing the data or cooperation through communication, we call it as inter-process communication, IPC. So this is called as IPC, making mechanism through which two or more processes can communicate with each other, either for sharing the data or synchronizing their communication. That is what we call it as inter-process communication. Now, is essential for process coordination. IPC is essential for process coordination, and the various type of IPC mechanisms adopted by process, and all the mechanisms, they are kernel dependent. So now we are going to discuss few of those mechanisms which can be used for inter-process communication. Now, the first and the simplest form of mechanism for making the processes within the system to communicate is the concept of shared memory. Now, this is the common memory through which you can make multiple processes exchange the information. So you can see the picture here are the process 1 and process 2, and the shared memory is also here, shared memory area. Now, what will happen? Say this process has something to communicate with the other process. Hello, please mute. This process has something to communicate with the other process. What it will do, it will just write the data, whatever it has, to the shared memory, and the other process will perform the read operation from the shared memory, and it will get the data. So this is how current. So this is how current you can make. Yes, yes. Please mute. So this is how you can make the processes communicate among themselves through the shared memory. And the simple primitives that are used here is the read and write primitive. We have one process which is the producer of the data. You can call it as the producer process. So I think in operating system, you might have studied. I don't know whether you've already studied it or not. So there is something called as producer-consumer problem. So producer is the process which produces the data, and consumer is another process which consumes the data produced by the producer process. And you have these two producer and consumer processes communicating through what the shared memory. And the shared memory there was a buffer, a small buffer that is created, a bounded buffer, and through that buffer you have the producer and the consumer processes communicating. And ultimately, this is same. Now here, instead of buffer, I'm calling it as a shared memory. And ultimately, where the buffer is present, buffer is also present inside the memory. So when I say buffered communication, it also is some kind of shared memory communication, because there the producer and the consumer both will be sharing the same buffer and also the same pointers in and out pointers. Now this is what the IPC mechanism through shared memory. So there should be some amount of memory which is shared by both the communicating processes, and then they can involve in communication or exchanging the data just by using the simple primitives like read and write. We have one process writing to the shared memory and other process getting the data by performing the read operation from the shared memory. So now, so different mechanisms adopted by kernel, by different kernel for implementing this, a few among are as follows. Called as pipe. So here I just mentioned it as a shared memory, and this shared memory can also be viewed as a pipe, or the shared memory can also be viewed as a memory mapped object. So now we focus on the pipe. So this you can view it as the normal pipe, which you people know, the normal pipe which is used for flow, allowing the water to flow. Now we will just understand the first mechanism, pipes. How do we make the processes communicate through the pipe? Now, what is a pipe? Pipe is basically a shared memory which is used by the processes for communicating. So now, why it is called as pipe? Because it has two ends. Now, the pipe has got two ends. We have one process attached to the one end of the pipe, and other process attached to the other end. Now we have one process acting as the reader and other process acting as the writer. What the writer will do, it will simply attach to one end of the pipe and keeps writing the data to that end of the pipe. What the other process will do, it will attach to the other end of the pipe and it simply keeps reading from the other end of the pipe. That means when I say a pipe, it has two ends. One is called as the right end, other one is called as the read end. And the writer process attaches to the right end of the pipe and it keeps writing the data to the pipe, and the reader attaches to the read end of the pipe and it keeps pulling the data out of the pipe. And it happens in first out manner, because the data or the byte that is first written by the writer process into the pipe will be available to the reader process first. So it happens in first in first out manner. So now, so that is what is a pipe. And again, pipe you have something called as unnamed pipe and named pipe also. Unnamed pipe, or else you can also call it as anonymous pipe. So no name given to the pipe. So basically, these unnamed pipes are used for making the processes which are residing within the same system to communicate and have some kind of parent-child relationship. So only those processes can be made to communicate through the unnamed pipe, because the pipe doesn't have any. Say there is a pipe created by the parent process, and this pipe can be used by its children processes to communicate with the parent. That is. So when I say unnamed pipe, So using that pipe, we can make processes which are residing on the same system to communicate, and with one more restriction. What is that restriction? So there has to be a parent-child relationship for the processes to communicate through the unnamed pipe or anonymous pipe. Any unrelated processes, say for example, the processes they don't have the parent-child relationship, so can they communicate using the unnamed pipe? It does not possible. Now, if you want to make unrelated processes to communicate, then you have to use a different pipe that is called as named pipe. So we'll understand that later. Yes, I need your response. Am I audible clearly?
Yes, sir.
Yeah, yeah. Now, and again, now I told two processors. Uh, uh, the process which is attached to the right end of the pipe, I call it as the writer process, and the process which is attached to the lead end of the pipe, I call it as the reader process. But there is one more terminology which you can also use. The process which creates the pipe, is called as the pipe server, and the process which connects to the pipe is known as the pipe client. So now we have two processes basically here. One is the writer process, and the other one is the reader process. Ultimately, the pipe should be created by any one of these two. Either the writer process should create it or the reader process should create it. Whoever creates the pipe, we call it as the pipe server. And whoever just connects to that pipe, we call it as the pipe client. And again,
Yes.
what about the direction of the data flow in the pipe? So it can be unidirectional or bidirectional. So if you have only one single pipe and we have the reader attached to one end and the writer attached to the other end, the communication can happen only in one direction. That is writer writing and the reader consuming the data. So the flow of data is from writer to the reader. So it is unidirectional communication. Now, what if I need bidirectional communication? Then I have to use two separate pipes, because if you use one pipe, it is only one direction. So it's I can compare this with the real pipe also, the real physical pipe. Now, using one pipe, is it possible for you to make the water flow in both the direction? It is not possible. Now, in one pipe, the water can flow always in one direction, either from left to right or right to left. Both the directions simultaneously it cannot happen. Now, similarly here also, the same concepts holds good. Now, if you are using only one pipe and there is a writer attached to one end of that pipe and the reader attached to the another end of that pipe, so the flow is only from what? Writer to reader. Now, what if I want to make the processes can behave, either as the reader as the writer. So, at some point of time, the process may behave as the writer, and after some point of time, it may act as the reader. Now, I need to support the bidirectional communication. What does that have to do? It is not possible through one pipe. So that case, I have to use two separate pipes. Two separate pipes. So we have two pipes. You can just imagine two pipes are there. So reader, is attached to one end of the pipe, and the writer, the writer is attached to the another end of the pipe. So when this reader, when this writer wants to send data to the other reader, it uses one pipe. And similarly, the process which was acting as reader earlier now wants to access the writer. What it will do, it will attach to the other end of the second pipe, the right end of the second pipe, and keeps writing. And the process which was acting as the writer earlier, now say it will act as the reader now and attaches to the other pipe and it will get the data. So if bidirectional communication is required, then you have to use two separate pipes. And the pictorial representation is also given here. So process one is writing. So this is the process. I'm calling it as a writer process, and it is attached to one end of the pipe, and the reader is attached to the another end of the pipe, and it's reading from the pipe. And the pipe can be named or unnamed. So when if I say it is unnamed pipe, so these two processes, what I'm saying here, P1 and P2, they should have the parent-child relationship. Now, if the parent-child relationship doesn't exist, then I have to go for using the named pipe. Using named pipe, you can make any process, unrelated process to communicate. So that we can do. Creating an unnamed pipe, there is a system called with the name pipe itself in Unix operating system. There is a system called with the name pipe. Pipe is a system call. And how do we create a named pipe? So there is a command in Unix with the name mkfifo, make FIFO. I hope all of you know mkdir, make directory. Similarly, there is a command called as mkfifo, make first in first out. Okay? If you execute that command, mkfifo and pass some argument to it, it will create a pipe file. What kind of a pipe file? Named pipe file. Because mkfifo followed by that, we'll be giving an argument. Say for example, my pipe. mkfifo my pipe. Now, what is that? My pipe is the name given to the pipe. And using that, since the pipe has got a name, so using this name, any unrelated processes can communicate. So luckily, implementation part is not there for you. So implementation. So I have done system programming, and in system programming, all these concepts will come. So for you, it is only the theoretical explanation, and the implementation part is not necessary. Even you need not remember the command what I told you. If you and pipe system for all these things, you need not remember. Next, yeah, that is what we are discussing now. The two types of pipe. One is what unnamed pipe or anonymous pipe. So anonymous pipes are unnamed. So unidirectional pipes used for data transfer between two processes. And I've written here only two processes, but please make a note. So they are used for making the only the related processes to communicate. That means the process should have the parent-child kind of relationship for communicating through the anonymous or the unnamed pipe. So the other one is the named pipe, so which can be created by using the command which I already mentioned you, mkfifo. Mkfifo is the command used. Now using that, you can go for creating a named pipe. So and this named pipe can be unidirectional or bidirectional pipe, or data exchange between any unrelated processes, between any unrelated process. That is what. Now, the process which again creates the pipe, here also whether it is a named or unnamed pipe, so we call it as a pipe server, and the process which just connects to that, we call it as a pipe client. So, and using this pipes, you can provide the point-to-point communication. So named pipes can be used for communicating between the processes running on the same machine, or the different processes running on the different machines also. So this is what is important. So unnamed pipes, they can be used to make processes which have the parent-child kind of relationship. And again, all these processes which have the relationship, they should be on the same system. But whereas using the named pipe, you can make either the processes which are residing on the same system or running on any different systems to communicate. So when I say one system is talking to the another system, it's not the system which is talking, it is the processes which are running on the system communicating with each other. We never say systems are talking to each other. The logic is saying the processes which are running on the systems are communicating with each other. Just go to the next slide. Next, this is you till now you understood named pipes and named pipes. So the other way of communicating through the shared memory is memory mapped objects. So memory mapped object is again a shared memory technique, and this particular technique is adopted widely used in real-time operating systems for allocating a shared block of memory, which can be accessed by numerous processes for simultaneous communication. This memory mapped object is widely used in real-time operating system. This is the kind of technique which is widely used in the real-time operating system for allocating the shared block of memory and making multiple processes simultaneously communicate. So in this approach, a mapping object is created and a physical storage for it is reserved and committed. So a mapping, this is the logical thing. When I say mapping object, it's the logical entity is created, and the physical storage is also reserved. Some kind of physical, say RAM memory is reserved and committed. That means it's fixed for that inter-process communication. So a process can map the entire committed physical area or block of it the virtual address space. So the physical memory area that is committed for making the processes to communicate, can be mapped to a virtual address space. Now, all read and write operation will not directly happen on this committed physical memory area. Instead, it's going to happen on this mapped virtual address space. All read and write operation to this virtual address space by the process is directed to the committed physical area. First, the read or the write operation will start from here, the virtual address space, and from this virtual address space, it gets communicated to the committed physical area, that is the actual memory location. The same thing is shown here pictorially. So this is what the physical memory, this is what the process 1 and the process 2. So we have, this is the memory. So you can observe this. The memory mapped object is mapped into process 1's virtual address space. And similarly here, the memory mapped object is mapped into the process 2's virtual address space. This is the mapping. And this is the commit physical memory. This is the physical memory. So before anything gets transferred to this, it is initially read or written to this virtual memory. From here, it gets mapped to the other place. Now, till now, you understood the shared memory mechanism for making the processes to communicate. So again, in the shared memory, you understood various concepts like pipe. Again, in pipe, two things: named pipe and anonymous pipe. And then you understood the mechanism, shared memory mechanism, which is most widely used in the real-time operating system, that is memory map objects. So next mechanism, the second IPC mechanism is message passing. So under shared memory, we discussed all these things. What are they? We understood, and memory mapped objects you understood. And again, under pipes, two types: anonymous pipes and named pipes. Now this is the second way of IPC mechanism, that is message passing. So message passing, again, it can be a synchronous or asynchronous information exchange. I'll highlight you what is the meaning of synchronous and asynchronous. And this we have already understood in communication interfaces. So few communication interfaces were synchronous communication interfaces, and few were asynchronous communication interfaces. There, when I say synchronous communication interface, clock cycle was used in order to synchronize the sender and the receiver. And when I say asynchronous, instead of clock cycles, we were using a common agreement, the predefined agreement between the sender and the receiver. So both sender and receiver agreed on predefined settings. So that is what we call it as predefined agreement. Now here also, in message passing also, we have something called as synchronous and asynchronous information exchange. And again, information exchange can happen within the process or across the threads also. The major difference between shared memory and message passing technique is, so this is what you're observing. In the shared memory, so lots of data can be shared. So you're able to exchange huge amount or the large amount of data through the shared memory, because all the processes, the communicating processes for sharing the common memory, and it was a simple operation. One used to write to the shared memory, and other used to consume from the shared memory. Now, when I say message passing, so there is no concept of shared memory here. So the message will be explicitly passed from one process to the other process. So the message. So say for example, I want to send an email. Now, internet works with the message passing technique. So internet will not work with the shared memory concept, because in internet, say if I want to send a message from my system to a system which is in some other place. So what is that I have to do? I got to send it as an explicit message. I got to make a message, and I got to address that message using the IP address and the port number on which the other process where the message is required is running. So now when I say message passing, it's not possible for you to send the large amount of data. What you can send is only the small amount of data. So in case of shared memory IPC, shared memory kind of communication, even you can go for sending the large amount of data. So that is one basic difference. Shared memory allows you to send lots of data, whereas message passing, so limited amount of info or data can be passed through the message passing technique. Message passing is relatively fast and free from the synchronization overhead compared to the shared memory. So in shared memory, you got to do a lot of synchronization. Because again, the shared memory, when I say it is a finite memory, if the sender is too fast, what is that you got to do? You got to limit, you got to make the sender block when the entire shared memory is full. And when the receiver consumes some data and makes the room for the what? It should consume some data, and it should make some room for the writer to write the next set of data to the shared memory. So some kind of synchronization is always necessary. And if the receiver is very fast than compared to the sender, So the receiver may try to read an empty shared memory. All these things. What you got to do now? You got to synchronize. When the shared memory is full, block the sender. When the shared memory is empty, block the receiver. So this kind of synchronization is required. But when I say message passing, the synchronization, so overhead is a little reduced, and there also synchronization is required. But it's not as complex as shared memory synchronization. Now, what are the different uh, message passing techniques? So we have these many. So message queues are there. There is something called as message queues, and there is something called as mailbox, and there is something called as signaling. So these are all the three different types of message passing techniques which you can use in order to make one process communicate with the other. And again, yeah. So we'll just go to the next slide and understand each one of this message passing technique. So message queues, the process which wants to talk to the another process. So what it does, it posts the message to a first in FIFO queue called a message queue, and a message queue also operates in this fashion, first in, first out. So so there, assume there's a message queue, and the process wants to convey something to the other process. What it will do, it will simply post the message to the message queue, and this message queue stores the message temporarily in the system, and also passes it to the desired process. So now, in between the two communicating process, the process 1 and the process 2, which are communicating, we have a message queue, which is providing the service in, first out manner. So now the simple diagram is also given here. So process 1 and process 2. What we have done. So this is not now a shared memory. It is a message queue. We have the message sent by the process 1. It goes and sits into the message queue, and same is received by the other process 2. Now, why I'm saying this is not a shared memory, because the primitives used here is not read and write. When I said a shared memory here, so the primitives that were used were read and write. So this is the small amount of memory which was commonly agreed by these two processes for communicating. And where is this memory found? This memory is found inside the user address space. And this writes to the shared memory, and this will read from the shared memory. But this message queue, what I'm telling now, this is not present inside the user address space. This is present inside the kernel address space. Now for this, so reading and writing, so sending data to this message queue cannot be done through the right system call or the right primitive. It can be done by using the send primitive. You can just observe here, send. So send. So this process prepares the message and just sends the message to this message by using the send primitive. This takes two parameters. Now, what is the first parameter? Obviously, the name of the process to which the message is to be sent. Here I've written the name of the process, but strictly speaking, it won't be the name of the process. It will be the ID of the process, because every process will have an unique identification number. So that is the ID. You got to specify as a first parameter to the send, the ID of the process to which the message is to be sent, and the second argument is the message itself. Okay, this. And say, what if say I want to send the message to the process which is running on a different system. So then it is not just the process ID. Along with the process ID, you've got to have the IP address also. It should be a combination of both IP address and the process ID, because you got to identify the mission uniquely within the network. To identify the mission uniquely within the network, what you require is the IP address, and again on you got to uniquely identify the process on which this message is to be sent, to which the message is to be sent, and that process on the destination mission you uniquely identify by using the process ID, or sometimes you also use something called as port numbers. Okay, let for now we'll assume it as port ID. Sorry, process ID. I hope people understood. Send. If you're sending to the process which is residing on the same system, so then this should be only the process ID. If you're using the send to send the message to a process which is running on a totally different system, then it should be a combination of both IP address and the port number. And similarly, the process on which the message is required, will make a call to the primitive called as receive, and it takes two parameters again. The first parameter is the name of the process from which the message is to be received. So the name of the process from whom the message is required, or ID of the process from whom the message is required. So in case if it is receiving the message from the process which is residing on a different system, then again even this should also go for specifying the combination of both IP address as well as the port number or the process ID. And then the message. So this message here in the send is a filled buffer, and this is an empty buffer. Message is pointing to an empty buffer. Is received when as and when it gets the message via the network. So the message is received and filled into this buffer. So this is a filled buffer and this is an empty buffer. Remember that. Now I hope you people understood it. Now if you have any doubts till here, you can ask me. Otherwise I'll proceed. Hello. Hello. Hello guys. Yeah, I'll proceed.
So you can proceed.
Yeah.
Yes, thank you.
Next is the mailbox. So you understood message queues. Now we are understanding the second technique of message passing, that is the mailbox. And so mailbox, to some extent, is similar to the message queue, what we understood in the previous slide. So that is the reason we say it is a special implementation of message queue, because it slightly differs from the message queue. Now, and the mailbox is usually used for one-way communication. But message queue can be used for two-way communication, both the way communication is possible. But mailbox is generally used for one-way communication, that is only a single message is exchanged to the mailbox, whereas message queue can be used for exchanging the multiple messages. One task or a process creates the mailbox here also. So one task will create a mailbox, and the other processes or tasks can subscribe to that mailbox. So whatever this, so this task is sending some message post to this mailbox, and it will be broadcasted to all the tasks which have subscribed to this particular mailbox. So and yeah, this is and a simple extension to what the message queues, and this is most widely used for sending the message from one task to many tasks. So one to many communication. Now, signaling is the third technique for what message passing. So message passing IPC mechanism. Third technique in message passing IPC mechanism, and this signaling is used for asynchronous notification mechanism. Uh, so signaling is mainly used for execution synchronization. When I say signaling, it does not for exchanging the information. So message queues and mailboxes are used for exchanging the information, but signaling is not meant for exchanging the information. Instead, it is used for synchronizing the execution sequence between the multiple processes, like who should execute first, and after that process, who should next execute. For this purpose, the signaling approach is signaling technique of message passing mechanism is used. So that's one. Signal do not carry any data and are not queued. So the signals are basically used for controlling the execution synchronization between the multiple tasks. Next is another type of IPC mechanism is remote procedure form. We understood the two types of IPC mechanism. One is shared memory mechanism. Under that shared memory mechanism, you understood pipes. Under that pipes, again, you understood two things: anonymous pipes and unnamed pipes. And another type of shared memory technique was memory mapped objects. And then we started discussing the second IPC mechanism, that is message passing. Under message passing, again, three techniques were there. One is message queues, mailbox, and then signaling. Signaling is not used for exchanging the data, but it is used for controlling the execution sequence among the multiple processes, or simply for controlling the execution synchronization among the multiple processes. Now, the third form of IPC mechanism is the remote procedure call and sockets. Let me talk on the RPC first. Remote procedure call, short form is also called as RPC. Sorry, in bracket I've written it as IPC. It is not IPC. It should be RPC, remote procedure call. So before going to the remote procedure call, let me highlight on LPC, local procedure call. All of you know this local procedure call. So you have written programs all these days, C programs, Java programs, all these programs, and you have written the functions. So calling the function that is written inside the C programming, and when you're calling that function within the same program, it is called as local procedure call. Now, what is remote procedure call? The procedure or the function which you're calling is not present inside the same program. It is present, it is the function which is present in a different process, and that process can be on the same system, or it may be running on the other system. That is what we call it as remote procedure call. So remote procedure call, again, it has some kind of inter-process communication mechanism, because here also we have one process remotely invoking the method or the procedure which is present inside the other process. Some kind of communication is happening. Hence, this RPC is also classified as a mechanism of what inter-process communication. And this mechanism, RPC, is used by a process to call a procedure of another process running on the same CPU or on a different CPU, which is interconnected via the network. So when I say the network, it could be a wired network, or it can be a wireless network also. So when I say wired network, it can be a LAN, or it can be a WAN, it can be a MAN. And when I say wireless network, it can be your Wi-Fi, or a WLAN, wireless local area network. Even it can be a simple Bluetooth kind of connection, or even infrared kind of connection also. So that is what. So that is what the remote procedure for. So now in procedure-oriented language, we call it as remote procedure call. But the same in object-oriented terminology, instead of RPC, remote procedure call, we call it as RMI, remote method invocation. Or simply, you can also call it as remote invocation. Because in object-oriented programming language, instead of calling them as procedures or the function, we call them as the methods. For that reason, in object-oriented terminology or object-oriented programming language, so RPC is called as remote method invocation. Now, the process or the CPU that is containing the procedure that needs to be invoked, we call it as a server. Because so that process has the procedure or the function that needs to be called, we call it as a server process. And the process which initiates the RPC request, we call it as a client. So that is the simple thing. So this is the third form of what IPC mechanism, remote procedure call. And of course, we have sockets also. Now I'll speak on the sockets. Now here, I think, yeah, sockets will come. Now what are sockets? Let me define it. Sockets are the software-defined endpoints through which two processes can communicate. So sockets are, hello, am I audible?
Yes, sir. You're audible.
Yeah. Now, sockets are the software-defined endpoints through which two processes can communicate. Now, I can give you a simple analogy. Say I want to charge my mobile phone. What is the name? I need a charger. Now, I'll be plugging my charger to the socket, electrical socket, and then the other end I'll connect to my phone. So my phone gets charged. Now, the socket, what I'm discussing here, is something similar to that, but it is not the physical socket. It is a logical endpoint through which two processes can communicate. Now, later I'll just draw a simple diagram and I'll make you try to understand. That is what is a socket, and using the sockets also you can make one process communicate with the other socket. So right now you are in fourth semester. I don't know whether in seventh semester, I think. Yeah, seventh semester. So in network programming subject, network subject, you have one lab, that is networks lab. There, he'll be doing the socket program. He'll write the programs, using the sockets, and you can make that program communicate with the program which is running on the other system, socket program. Socket system call is there, bind, and then there is listen, something called as listen system call, and then accept system call. So many things. So, but the program is not there for you. So implementation part is not there for you. Only the theoretical part. Let me focus only on that. Uh, in order to make RPC communication compatible across all platforms, it should stick onto the certain standard format. So compatible issues will happen because the platforms are different, hardware architectures are different. We are saying remote procedure calling a procedure which is running on a different process, and that process would be running on a different system with a different hardware architecture, different operating system. So there is always what the platform incompatibility. So, but still the RPC remote procedure call should work efficiently. Now for that, so it provides something called as interface definition language (IDL). Defines the interfaces for the RPC. So whenever you are trying to make RPC remote procedure call, this is what the standard is going to be using. Interface definition language, and this IDL will mask all this kind of heterogeneity or hides all this kind of heterogeneity. That is different operating systems, different hardware architectures. All these things will be efficiently masked by the interface definition language. Now, what this IDL will do is it will generate something called as the client stub and the server stub, and these stubs which are generated by the interface definition language will efficiently mask the heterogeneity, and they provide the efficient communication. Now, one example is Microsoft provides this. Microsoft Interface Definition Language (MIDL) is the implementation from the Microsoft for all Microsoft platforms. Again, Microsoft also heterogeneity is there. So because some people might be using the Windows 7 as their operating system, and some may be still on the older operating system like Windows XP, and some may be using Windows 10. And again, the many tools are available. Say, for example, when I say the server softwares, Apache Tomcat is there. I don't know whether you people know this softwares or not. So Apache Tomcat, the version that is compatible with Windows 8 is not compatible, with Windows 10. So all these things are there. Even with the Microsoft, so there are a lot of Microsoft products itself or the platforms itself, there is a lot of incompatibility. All those incompatibility can be efficiently masked by using the MIDL. Yeah, and RPC communication can be either blocking or non-blocking. So blocking we call it as synchronous, and non-blocking we call it as asynchronous. When I say blocking, the fast sender, the moment the buffer is full, it will be prevented. It will be blocked. So and when I say asynchronous, so it's non-blocking. Even if the buffer is full, the sender will not stop sending the data. It keeps sending the data, and what is the result of it? The data that is sent after the buffer is full will be lost. So if you don't want anything to be lost, then you got to make RPC communication as the blocking communication. Now here I have the example here. So this is the process which is running on one CPU, and we have the process running on the other CPU, and this process has some kind of a procedure. Now, and this RPC, remote procedure, this procedure can be called by using TCP/IP, that is Transmission Control Protocol, or UDP, User Datagram Protocol, over the socket. Socket, as already told, it as a software-defined endpoint through which two processes can communicate. And how to create a socket? There is a system called within a socket. Using that, you can create a socket. And after the socket is created, the socket must be immediately binded with the IP address and the port number. And once the IP address and the port number is binded, the processes can involve themselves in communicating. Now, transmission control protocol, I hope you might have studied already this in the networks. It is a connection-oriented transmission protocol. That means between the sender and the receiver, there will be a logical connection established, and all communication. Please mute. Hello. Please mute. Hello. So all of you, please mute. Yeah. Still not muted. Yes. Akshay Kumar. Akshay Kumar. Yeah. Thank you. Okay. Now, TCP, I was telling, Transmission Control Protocol, it's a connection oriented service protocol. Why we say it as connection oriented? Because I say I have a source and a destination. So what will happen? A logical connection will be established between the source and the destination using the routing algorithm and all those things. A logical shortest path will be found and a logical connection will be established. It's not a physical connection, a logical connection will be established. And if the source is sending 100 packets, all the 100 packets that is sent by the source will take the same path to reach the destination. So, and in UDP, user datagram protocol, this is a connectionless protocol. Why we call it as a connectionless protocol? Connectionless, since we say connectionless, that is unreliable. Connectionless protocol because there is no logical connection established between the source and the destination. So if the source is sending 100 packets, there's no guarantee that all the 100 packets will take the same path to reach the destination. Each packet can take its own path to reach the destination. For this reason, there may be the possibility of few packets getting lost, and even the packets, which reach the destination will be out of order because the packet which is sent first is taking a longer path to reach the destination, and the packet which is sent next, or the second, is taking a shorter path to reach the destination. So there's possibility of destination receiving the first packet first compared to the first one. So there's a possibility of packets received by the destination out of order also, and the rearranging mechanism is necessary. But when I say this TCP connection oriented, since the logical connection is established between the source and the destination, so logical connection you can assume it's something like a railway track between the source and the destination. You put the objects on the track, so all the objects one after the other they take the same path to reach the destination, and there is no question of what the packets getting mixed or the packets getting delivered in out of order sequence. All the packets will be delivered in the same sequence that is sent by the sender. So hence we say TCP is more reliable than compared to UDP. So this whole concept will come in networking. So we'll not go into much details of all those things now. We'll just study what is required for us. Okay. Now sockets, yes, I already told, is a logical endpoint through which two processes or two applications can communicate. And again, when I say socket, once you create this socket, the socket must be binded with the IP design, the port number. And sockets can also be, you can create two types of sockets. Say, for example, I need connection-oriented service. I want to use the TCP protocol. Then you should go for creating a stream socket. A stream socket is nothing but the TCP socket. So, two types of sockets, internet sockets. One is the internet socket, another one is the Unix socket. So internet sockets, INET, it's short form, it's also called as INET. So if you are creating the socket for making a process which are residing on two different systems to communicate with each other, then you should create an INET socket. So this is the parameter which will be passing as argument to the socket system. Now, if you want to make the processes which are residing within the same system to communicate through the socket, then you need not create an INET socket, internet socket. You just create a Unix socket. So you can just say it as Unix, or else you can also call it as there is another name for this, the local socket. That is this is something called as address family also. Sometimes we call it as AF underscore INET. AF underscore Unix or AF underscore local also. So AF stands for address family. So this is what you have to keep when you are writing the program. Since we are understanding this conceptually, So all that syntax is not necessary. You just remember it as internet socket, that is enough. But while writing socket, system call socket and open the flower bracket, sorry, open your small parenthesis, and when you're writing the parameter, you cannot just write it as inet, you got to write it as AF underscore inet. So okay, now you just remember this as inet, that is sufficient. When you are going to use this socket, when you want to make the processes across the different system to communicate, so it must be inet. So, and if you want to make the processes within the system to communicate, only within the system to communicate, then you can make it as Unix socket or local socket. Now, is it not possible to make the processes which are residing within the same system to communicate through inet? Yes, it is possible. But if you're using inet for that purpose, then it will be little slower. Why little slower? Because it will make use of all the 7 layers of the OSI reference model. So, when the communication is happening between two different systems, if all the 7-layered OSI reference model comes into picture, that is okay. When you are making the processes which are residing within the same system, what is necessary for you to use all the 7 layers of the OSI reference model? So that way, it will make it little slower, but inet can also be used for making the processes which are residing within the same system to communicate. But so generally, we prefer using the Unix sockets of the local socket, because that way it is much faster, because many of the OSI layers will be bypassed, because the communication is required only within the system, and that way it will be much faster. Now, inet socket, this I've already told, for used for internet communication protocol. That is when you want to make the processes residing on two different systems to communicate. And again, inets are classified into two things: stream sockets and datagram sockets. So I want the reliable communication or reliable communication. So then you have to create the stream socket and the protocol. When you create the stream socket, so the protocol that will be used is TCP. TCP is the protocol used. Now, this the first parameter to socket will be this AF underscore inet, and the second parameter to socket will be the type of socket required, whether you require a stream or the datagram socket. Now, if I need a stream socket, then I'll be writing it as stream. I'll just use Notepad and write you, because you'll understand. You'll get an idea how it looks. I have the Notepad already here. It's something like this. Socket is a system call. So first parameter which will be giving is AF underscore inet, comma, and the second thing is string, like this. Hello, able to see my screen?
No, sir.
This, oh, I think I have shared only a PPT. Okay, let me write in the PPT itself. I'll just close this. Yeah, insert one more slide. Yeah. Now you're able to see? Hello?
Yes, sir. Able to see, sir.
Yes, sir. Yes, sir.
I'll just write here. Socket, SOCK, socket. So first parameter is AF underscore inet. So this says I'm creating an internet socket. So because I want to make the process residing on two different systems to communicate. And the second parameter is sock underscore stream. And the third parameter is also there. We make it as 0. So this is how you'll be writing. So doing like this will create an inet socket, and what kind of socket again it is? A stream socket. Now, since I've told it a sock underscore stream, which is the protocol that will be used, TCP is the protocol that will be used. And you have between the source and the destination a logical connection established. In any number of packets the source sent will take the same path to reach the destination. And this we are making it as 0 because since the socket type I've told it as TCP socket or the stream socket, you can also call it a stream socket or TCP socket. So the by default the protocol that will be used is the TCP protocol. And similarly, if I want to create an UDP socket, so let me copy and paste this again instead of writing. sock underscore dgraph. So this creates you the datagram socket, and which is connectionless and unreliable socket. That means the packet sent by the source will not take all the packets sent by the source will not take the same to reach the destination. They take their own path and they reach the destination. And in this way, the many packets may get lost. Sometimes the packet will be delivered out of path. So this. And what if I want to create a socket, local socket, like this again, AF underscore, instead of inet, I'll be writing it as Unix, or AF underscore local. So both are correct. You can go for using this or this if you want to make the processes which are residing on the same system to communicate. I hope people understood. Got an idea of the sockets?
Yes, sir.
Yeah, I can write you the simple diagram also and show you. Let me go to insert shapes. Not this. Now, assume this is a computer, one computer. I'll take another one. Sorry. So this is another computer. I'll just take a process. The process running on this. I have another process running on this. So this is mission 1. Let me call it as or give some IP address. Let me give some IP address to this. Add text 192.168.0.1. For this one, let me give the IP address as add text 192.168.0.2. So IP address comes in 4 octets. I hope you people know this. And then text, let me call this as process P1. And let me call this as process P2. So I'll just explain this concept and stop for today because already it is 12:38. Let me finish this and stop. I have process. Now what will happen is, so there will be a socket created. I'll show you. So this creates one socket. This is a logical endpoint. And there is one more that will be created. So logical, this is socket for this, and this is socket for this, and they will be connected. And this socket here will be binded with this IP address and the port number on which this process is running. And this socket here will be binded with this IP port number on which this process is running. Now, and whatever this process sends to this socket will go to this. And whatever this sends to this socket will go to this. This is how they involve in communication. I hope you people understood till here. Hello?
Yes, sir.
Yeah. Now, let me stop here. See, I'll remember this is the 16th, the 15th slide number 15. Okay. From tomorrow, I'll continue from here, the task synchronization. So till now, I've completed the task communication. So next thing to start is task synchronization. So, in my next class, I'll go with this. Yeah, thank you. And today, I think 50 participants participated. Just inform other students also to make time and attend the online class. Just inform your friends, huh?
Okay, sir.
Yeah, yeah. And thank you all.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.